Every single breakthrough in AI today feels sudden. A new model drops almost every week from one of the leading AI companies in the world like OpenAI or Anthropic. And a lot of people freaks out because the world could literally change overnight, as it already did because of AI. But the truth is, nothing in AI has happened overnight. Behind every revolution, there is an elegant idea formalized in a research paper which paved the way for the remarkable progress that we are experiencing today. So, in this video, I will walk you through 7 research papers that together I think tell the true story of modern AI. And just to be clear, this is not about the hype, not about the press releases, but the funnel of actual scientific milestones that made today's breakthroughs possible. We will start with how machines first learn to represent meaning, then move through architecture, scaling, grounding, and finally reasoning. And by the end of this video, you won't just know what these papers did. You will see how each one connects to the next one, how the field evolves step by step, and where the next big leap may come from. So, let's dive in. Paper number 1, Efficient Estimation of Word Representations in Vector Space. Before 2013, language models treated words like isolated atoms. Each word was one hot vector, basically a long list of zeros with a single one somewhere. It technically worked, but semantically, it meant that cat and dog were just as unrelated as cat and quantum. There was no notion of meaning for words in a sentence, just their position. And then came Thomas Mikolov and the Word2Vec paper. And here is when things shifted. It didn't just improve how we store words, it changed what it means for machines to understand them. Word2Vec introduced dense vector embeddings. Instead of sparse, meaningless one-hot vectors, every word got a position in a continuous space, a sort of landscape of meaning. Words that shared context ended up close together. Not because we taught the model to do that, but because it discovered that structure on its own, just by predicting which word appeared next to each other. And that's the beauty of it. No manual labeling, no linguistic rules, just data, and from data, meaning emerged. So for the first time, the geometry of language made sense. I remember very well how intrigued I was the first time that I saw this kind of image. You could literally do math on meaning. The classic was king minus man plus woman equals queen. And that single thing became an icon, a proof that semantics could be captured numerically. Under the hood, there were 2 clever training setups, skipgrams and continuous back of words. One predicted context from the target word, the other predicted the word from its context. Both were early forms of self-supervised learning, the same principle that drives GPT and BERT today. But beyond the math, there is something philosophical here. This paper turned a representation into the foundation of understanding. Every modern model, transformer, GPT, BERT, you name it, starts by mapping the words into vectors that trace their DNA back to this word. Word2Vec was the first time we realized that understanding language isn't about memorizing rules, it is about discovering relationships. And that realization changed everything. But once machines learned to represent meaning, the next question was, how do they move beyond understanding words to understanding the relationships between them? Paper number 2, Attention is all you need. Well, recurrent neural networks, or RNNs, was one of the most popular deep learning architectures in the last decade. The problem is that it was painfully sequential to work with them. You will have to wait for the processing of the previous sequence to finish every time. And the longer the sequence, the more memory you lost, which means that the gradients started to vanish and context started to fade. Now, imagine this. Instead of crawling through text step by step, what if every word could see every other word instantly? No loops, no gates, just direct connections between all tokens in a sentence. That is the core idea behind the transformers architecture that they propose. The idea of self-attention. So basically, you just need to compute for each token how much it should attend to every other token in a sequence of text. Then you get the weighted map of relationships between tokens, which you can think of as a web of dependencies built from the data itself. And this is how the model learns that bank means something different in private bank versus central bank. But I think the major breakthrough of this technology was not the attention mechanism itself. I think it was the fact that attention can be computed in parallel. And because of this, the transformer could finally take full advantage of modern hardware like GPUs or TPUs or you name it. No recurrence, no bottlenecks, just clean matrix multiplication power, and that shift made scaling possible. Training on billions of tokens became less of a research problem and more of an engineering challenge. And that's the part most people miss. Transformers didn't just open for RNNs. They turned language modeling into a hardware problem you could scale. The faster your chips, the smarter your model. And since then, every model, even models in vision and biology, trace back to this architecture. So while word-to-vec gave machines a way to represent meaning, the transformer gave them a way to reason about it, all at once, and all in parallel. One paper that replaced loops with links and turned numerical attention into the new currency of intelligence. So the transformer gave us architecture, but as you may know, structure alone isn't intelligence. So what if instead of training models for every tiny task, we started want to understand everything? And this question leads us to our next paper. Paper number 3, Improving Language Understanding by Generative Pre-training. By 2018, we have something powerful. Transformers could represent and connect words like never before. But there was still a missing piece. We were still training models the old way, one narrow task at a time. For example, if we wanted to do sentiment analysis or translation, we had to train a specific model from scratch for each of these tasks. Then came a quiet paper from OpenAI that changed the entire training philosophy. It asked a simple but radical question. What if instead of training for a specific task, we train a model for understanding everything? The method was called Generative Pre-training, or GPT for short. And here's the idea. First, you take a massive amount of raw text and train a transformer to predict the next token. No labels, no supervision, just context predicting what comes next. And that is pre-training. Then, once the model has acquired the structure of language, you fine-tune it on a smaller labeled dataset to perform a specific task like question answering or sentiment classification. And this pre-train, then fine-tune pipeline sounds obvious today, but in 2018, it was a paradigm shift in the field of AI. Because What this paper proved was stunning. A model trained purely on next token prediction could already write, translate, summarize without ever being explicitly taught to do those things. In other words, capability emerges first from self-supervision, not from labeled data. The broad, unsupervised exposure to language builds the foundation. Fine-tuning just shape it. So this is the paradigm shift. You don't need to handcraft intelligence task by task. You grow it, and then you guide it. That single insight became the operating principle behind every LLM model since then, from ChatGPT 2 to the latest ChatGPT 5 that we had at the time of recording this video. So, pre-training gave machines raw capabilities, but it also gave us a new problem. If models can learn from the entire internet, how do we make sure they learn what we actually value and interact with us in the way that we actually like it? Paper number 4, learning to summarize with human feedback. By 2020, models were powerful. I could say that they were too powerful in a sense. They could generate language fluently, but not always trustfully, safely, or in ways that matched human intent. They didn't lie maliciously, they just didn't care, because until then, we trained them only to predict text. And as you may know, the internet is actually a wild place full of biases and rage-bait comments. We really needed to align those models with positive human judgment. And that is when OpenAI released a transformative paper titled Learning to Summarize with Human Feedback. On the surface, it looked simple, a summarization task, but under the hood, it introduced a profound paradigm, reinforcement learning from human feedback. Here is how it works. You start with a pre-trained model that generates multiple summaries from the same text. Then a human ranks the quality of those outputs. The model then uses those rankings to learn what humans prefer. In other words, you train a reward model from this human data and then use reinforcement learning to fine-tune the base model so that it optimizes for that human-aligned reward. The result is that the model doesn't just predict the likely next word in the sentence. It predicts desirable text. It learns to write in ways that align with our sense of clarity, helpfulness, and tone. And this was more than a summarization paper. It was a turning point because it quietly solved a moral question behind AI. The question like, how do you make a machine not just intelligent but aligned to positive human values? And since then, every conversational model you have used from ChatGPT to Claude to Gemini stands on this foundation. So with alignment, models became much better than before. But power was still limited by scale. So researchers started to ask the following question. What if intelligence itself could be predicted like a physical law? And the answer to this question came in the following paper. Paper number 5, Scaling Laws for Neural Language Models. By 2020, something strange was happening in AI labs. Every time researchers made a model bigger, for example by adding more parameters, feeding with more data, or using more computing, the models just kept getting better. And the interesting thing is that there wasn't a clear reason of why this happened. So a group of OpenAI researchers decided to study and measure this phenomenon more precisely. They trained language models of various sizes on controlled datasets and track a metric of performance called loss, which is a numerical value that quantifies how far the model predictions are from the actual target values during training. And what they found was shocking. When you plot performance against model size, dataset size, and compute, what you get is a power law. And this means that each dimension, parameters, data, computing power, followed a predictable, almost mathematical relationship with performance. So if you double the parameters of the model, you increase the training data, then you should expect a predictable gain in model performance. And that insight changed the AI strategy of the leading companies in the field, because suddenly training wasn't guesswork anymore. It became engineering. You could plan your model like you would plan a rocket launch. You could know precisely that given this much computing and data, you will get the expected results. It also revealed a deeper truth. Model quality wasn't limited by architecture, but by scale and by the resources you were willing to put into it. And that realization started the arms race of modern AI that we are living today. From GPT-3, Palm, Gemini, Claude, all of them are products of this law. Each one just kept climbing the same curve. So scaling law told us that bigger really is better when it comes to training LLMs. But grow without grounding is dangerous. So the next step was clear. Connect models to the real world. Paper number 6, Retrieval Augmented Generation. By 2020, large language models started to be a big thing. They could write essays for you, answer all kinds of questions, and even reason to some extent. However, every LLM output came from patterns learned from their training data, which was actually a frozen snapshot of the entire internet. If you ask them about something new, they confidently invented an answer, something that we call it hallucination. I made a video about this some time ago, and I will lay you a link in the description down below if you want to check it out. So, that's when Facebook AI, now Meta, proposed a clever fix in the paper titled Retrieval Augmented Generation, or RAG, to be sure. The idea was quite elegant. Instead of relying only on what is inside the model's parameters, we should be able to let the model look up for the new things. RAG combined two systems, a retriever, which searches an external knowledge base for relevant documents, and a generator, which conditions its answer on that retriever text. In simple terms, it gives the model access to fresh, factual, verifiable information, making that much more reliable. Technically, RAG uses a dual encoder architecture. One network encodes the query and another encodes documents. Both live in the same vector space, so the system can fetch the most semantically relevant passages on the fly. And those passages are then fed into the language model as additional context for generation. It is retrieval plus generation, or memory plus imagination, and that changed the game, because suddenly language models could step outside their own frozen knowledge. They could interact with databases, APIs, the whole web, making them capable of updating faster than they wait. So this paper is the foundation of modern systems like ChatGPT with browsing capabilities, and every retrieval augmented assistant used in the industry today. So if scaling laws show us that intelligence grows with size, RAG taught us that truth requires connection. And so now that models could reach out and retrieve knowledge, a new question emerged. Could they also learn to reason, to think through problems step by step like we do? Paper number 7, Chain of Thought Prompting Elicit Reasoning in Large Language Models. By 2022, something fascinating has started happening. Language models could answer questions, summarize books, even write code. but they still stumble on one kind of task: reasoning. For example, if you ask a model a question like, in this example over here, the cafeteria had 23 apples. If they use 20 to make lunch and brought 6 more, how many apples do they have? Then the model would give you the wrong answer. Not because it lacked information, but because it wasn't thinking through the steps. And then came a paper from Google Brain that changed how we talk to these models. And the authors discovered that if you prompt a model to show its reasoning step by step, the accuracy of the model on complex tasks skyrockets. Math problems, logic puzzles, symbolic reasoning all improved dramatically with these techniques. Why? Well, because forcing the model to articulate its intermediate thoughts activates pathways that would otherwise stay dormant. So we discovered that for an LLM, it is not just producing an answer, it is unfolding a narrative of reasoning through it. And this was the moment LLMs stopped being autocomplete engines and started behaving like problem solvers. Chain of thought, or COT, reveal a major property. Reasoning can surface from a scale, but it needs the right conversation to come alive. Think of it this way. Self-attention gave model awareness of context. Retraining gave them word knowledge, but chain of thought gave them a structure, a way to organize thoughts itself. And the beauty is, this change came not from more data or compute, but from how we communicate with the model. And this is a reminder that intelligence isn't just architecture, it is also about behavior. Today's reasoning models, from Gemini to ChatGPT, trace their lineage directly to this insight. That sometimes to make a model reason, you don't build a bigger brain. You just teach it to think out loud. And that is where we are today. Models that can represent, connect, align, scale, ground, and even reason. So if you look at them together, you don't just see technical milestones, you see a story. Representation, architecture, paradigm, alignment, scaling, grounding, reasoning. It is not just a chronology, it's a philosophical progression from learning words to forming thoughts. Each paper didn't just build on the last, it expanded what we meant by intelligence. From vectors to values, from memorization to meaning, from output to understanding. And in that sense, the evolution of AI mirrors our own. We, too, started by naming things, by representing the world. Then we built structures of thoughts, found ways to align with others, learned to scale what we know, to ground it in truth, and finally to reason. Now, with multimodal models that can understand images, audio, or video, together, we have also agents capable of acting in the world, not just describing it. And we are seeing glimpses of neural symbolic hybrid systems that blend raw neural intention into a structured logical reasoning. So finally, I believe that if the last decade was about scaling intelligence, the next one will be about shaping it, teaching AI not just to predict or reason, but to understand us responsibly. And that's all for today. See you in the next one. Bye.